Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to look at, this is a continuation, section 4.4 in our text. We're discussing the orthonormal bases. And we decided we're going to call orthonormal ON, orthonormal bases. And soon we're going to get to Graham-Schmidt. So orthonormal bases, and what I want to do is let's derive the rotation matrix. The rotation matrix in R, the rotation matrix in R2, and see why it fits in this section. Okay, I think this is an interesting problem. So here's what the rotation matrix might do. So I'm going to just draw a set of axes. And let's draw a vector. So maybe here's my first vector. Okay. And I'm going to rotate it. I'm going to rotate it to, well, now that you can, let's see, I don't know, maybe we'll rotate it. I should be careful how I draw this. Let's rotate it to there. Okay. So what we're going to do is, let's label these. So we initially have some angle alpha. But what we want to do is we want to rotate this by theta degrees. You could use radians. I'm going to use degrees. Then we're already at some angle alpha, so we don't get to use our trusted baseline. And let's do one more thing. Let's say that, let's call it, I'm going to use another color just to provide some clarity, is this angle, the total angle, alpha plus theta, we'll call this the angle of beta. Okay. Well, let's think about this. So I'm going to take the vector v. I'm going to start with the vector v, and I want to move it to v prime. That's my goal, and I want to do it with a matrix. So find the matrix A that rotates v theta degrees. All right, we can do that. Well, we're in R2, and so we know that A has a general form. Let's just write the most general form. We know that A is going to be just some A, B, C, D. I'd sure like to do more, but I don't know how to do that yet. And here's what we know. We also know that if I take A and I multiply it by V, I want to get to the vector V prime. Okay, so this is our goal, our goal or underlying idea. How do we do that? Well, let's go back to some simple trigonometry, and that is that let's see, I've got so many colors available and probably so many going. So if I draw this right triangle using V, well, I know that V has an x coordinate of, see, I always have to think about this, of cosine, right? So remember that cosine of alpha, I'll do this here, let's just write that. So remember that the cosine of alpha would equal the opposite, adjacent side, divided by the hypotenuse. Well, let's see, what do we have? The adjacent side is x, we'll call it x. And then the hypotenuse is the length of the vector v. So there we have it. So our first coordinate here in our vector v is x equals, you know what, let me do a little bit of multiplying here. So then this just says that the length of v times the cosine of alpha equals x. Okay, and so that's this point right here. This is the length of v times the cosine of alpha. And then if we track v back over here to the y-axis, well, what do we have? Well, we could say then this. We could say that the sine of alpha is equal to the opposite divided by the hypotenuse. Well, we're trying to find some y value, so our opposite is the y length divided by the length of v. And so with a little bit of cross multiplication, or just clearing the common denominator of the length of v, we could say that y is equal to the sine of alpha, I'll write it this way, is equal to the length of v times the sine of alpha. All right, well, there we go. We've got the vector v. So, but you know what? We can also, I would encourage you to do this. I'm going to do this a little bit faster now, and I'm going to do it in orange. And that is, we could also find v prime. So v prime would have the coordinates. It would have an x coordinate then of the length of, well, it should be the same length. So the length of v cosine of beta, that big angle is where it's at, cosine of beta. And it would have a y coordinate of the length of v sine beta. And there we go. We now have almost everything we need to make this derivation. So let's come back up to our top. Let's go back to our white. So I have that A times B, or A, B, C, D. This is the matrix of A. Times the vector v. V, we said, is the length of v times the cosine of alpha, and then the length of v sine of alpha. And this has to equal, somehow, we're going to get this to equal the length of v cosine of beta, the length of v sine of beta. Okay? Well, let's just multiply the left-hand side. This is going to give us a system of equations. So this is just going to be A times the length of v cosine alpha plus B, the length of v sine alpha, equals the length of v cosine of beta. And now look at this. This is a vector. Clearly it's not the zero vector, so I'm going to say that the length of v is just not zero, because this wouldn't be interesting. So if I do that, now I'm left with this problem. A cosine of alpha plus B sine of alpha equals cosine of beta. But what is beta? Beta is the same thing as alpha, or as theta, plus alpha. Okay, now here's where we got to think about this, because there's a trig identity, and I find trig identities difficult to remember, difficult to derive. This one's worth remembering, and it says this. So I have A, I'm going to write a little bit smaller so I can get this in here, A cosine alpha plus B sine alpha equals, so the cosine is cosine theta, cosine alpha, and then you change the sign, minus sine theta sine alpha. Now, this is, there it is, we're done. Now you may be thinking, nope, don't see it. And that's okay, because look at what you're doing. Now you're matching coefficients. You're matching coefficients. In other words, the cosines have to add to a cosine. The sines have to add to a sine. Well, the way you do that is this. In other words, cosine theta cosine alpha, the only way to make that true is over on the left-hand side if A cosine alpha is the same. And clearly, if you look at the green, if you have a minus sine theta sine alpha, this has to match up with b sine alpha. And you're just picking it by the sine alpha component, the cosine alpha, cosine alpha. So what this says is this. This says that a cosine alpha has to equal cosine theta cosine alpha. Well, in other words, a is cosine of theta. And if you continue that, this also says, and it says that b times the sine of alpha has to equal minus the sine of theta sine of alpha. Well, wait a minute. If the signs match, then that means that b has to be minus sine theta. And there it is. We've done it. I'm going to leave C and D for you to do. It works exactly the same, and you should try that. The final result should be that A is equal to the matrix of cosine theta sine theta minus sine theta cosine theta. And that is A, the rotation matrix of a vector V in R2. Well, based on what we've learned, I think we need to go to another screen and we need to talk about orthonormal bases. So let's do that. So I'm going to come over here to a new screen and let's write this down so we have it. Our rotational matrix again. That's the cosine of theta, sine of theta, minus sine theta, cosine theta. Now, so far we've been working with matrices with just numbers. This is a matrix of functions, which actually makes it kind of interesting. So in other words, we want to check for an orthonormal matrix. Maybe it's not. It may not be, but let's just check. So the first thing we want to do is, and I'm going to call this, because we don't know yet. So our first column is A1, our second column is A2. So the first thing you'd want to check is A1 perpendicular to A2? I'm going to put a question mark, and then we're going to try. Well, that means that I would take cosine theta sine theta. So that A1 transpose, this is just A1 transpose, times A2 minus sine theta cosine theta. Well, that is equal to minus cosine theta sine theta plus, let's see, whoops, I just lost track of where I was at. Cosine theta, oh yeah, so cosine theta minus sine theta, I'm sorry, plus we're going to have a sine theta, cosine theta, and look at that, those just equal 0, so we can say, so A1 transpose A2 equals 0. Those are perpendicular. All right, now the next thing we want to do is check the length. So let's find the length of A1. And I'm going to work with the length squared, because if the length squared is 1, then the length is also 1. So that just says you take the first component, that's the cosine of theta squared, plus the second component, that's the sine theta squared. Well, if you remember our Pythagorean identities, you'll remember that that is 1. The square root is 1. A1 works. And you can also work on that to find out that that is the same for the length of A2 squared. Okay, so in other words, A is an orthonormal basis. Orthonormal matrix. Orthonormal matrix. Okay. Let's try an example using the matrix of A. So we need a few things. Suppose we want to rotate A. Suppose theta is 60 degrees. Suppose theta is 60 degrees. And B is the vector of 0, 1. Write B as a linear combination of Q1 and Q2. Now you may say, well, wait a minute, where in the world did Q1 and Q2 come from? Well, really, Q1 and Q2 are A1 and A2 in this case. Those are the same things. So what we want to do is we want to say, how do we write B as Q1 times Q1 transpose B plus Q2 times Q2 transposed B. All right, and then we're going to go back and graph it here in a little bit, I think. So how do we do this? Well, let's see. Q1, so let's do this. So I'm going to call it the A of 60 degrees. So the cosine of 60, I always have to think about this as a half. The sine of 60 degrees is square root of 3 over 2. So the sine of 60 is, and the minus is going to be minus root 3 over 2. And the cosine of 60 again is 1/2. Okay, so now we can follow this process that we did in the earlier video. So let's find this. So first off, we need Q1 transposed B. Well, that's going to be the Q1 transpose is 1/2 and root 3 over 2 times B, which we said is 0, 1. So this is going to give me the scalar of root 3 over 2. Okay, and let's continue this. So then I can say that Q1 times Q1 transposed B is equal to 1/2 square root of 3 over 2 times the scalar of the square root of 3 over 2. And we could factor out a 2 if we wanted to and write that, but we'll just leave it that way. And then let's repeat this. So now if we take Q2 transposed B, well, that's going to be minus root 3 over 2, 1/2, times B, which is 0, 1. And so that's going to give me this scalar of 1/2. And then if I take Q2 times that, Q2 transposed B, Q2, that's going to be minus the square root of 3 over 2, 1/2 times half. There we go. We've done it. So in other words, B is equal to, what do we have? It's equal to the vector of 1/2 root 3 over 2 times square root of 3 over 2 plus the vector of minus square root of 3 over 2 and then 1/2 times 1/2. So you might be wondering, you're like, well, what has this done? And what does this really look like? Well, let's just take a look. Let me just see if I can draw this for us. Let's see if I can draw this. Hopefully that looks good. Okay. Okay, there's my first basis vector. And here's my second basis vector. Okay, there we go. Now, if I've done these right, what would happen is these would look just like they're on this perfect circle. Actually, I don't know, it might have been pretty close to get enough to get the idea. And so here's my basis vector. So Q1 or A1 is 1/2 and then √3/2. And that really shouldn't surprise you, being that this is a √3/2. I'm going to have a lot of stuff going here. And then I, because these are just 30, 60 right triangles. And then Q2 is minus √3/2. So that'd be right here. Minus √3/2. And then this is going to be 1/2. Okay, those are my basis vectors. Now B is this blue vector. B is this vector right here. Why that didn't line up? How about right there? Okay, and so what does this say? So it says that you take the Q1 vector and you're going to scale it back by the square root of 3/2, which is about, let me double check, I think it's about 0.8, but I should just double check. So square root 3 divided by 2, 0.86. So this is about 0.86 of Q1. So that is the component from the Q1 vector. And then from the Q2 vector, if we scale this back, he says it's about half. It's about half of the Q2 vector, which is about, okay, so my scales are off, is about right there. And so this is the amount of Q1 and Q2 that add together to form the vector B. Okay, and that is an example of not only is the rotation matrix an orthonormal matrix, but also how to use the columns, the independent columns of the rotation matrix to write any vector as a linear combination of those vectors. All right, I hope that helps. Thanks for watching.